welcome, Baptiste. So we introduce now a new lecturer, Baptiste, and maybe also Boris from University of Leuven, and they are working together with Pierre. They are teaching assistants, and they will now show you an exercise to process, I think, Sentinel-2 data or optical data, again for live area index retrieval and applications of crop mapping using not Snap, but Jupyter Notebook. Is it correct, Baptiste?
Exactly.
Okay, the floor is yours. Thanks.
Thank you very much. Hi, everyone from Riga. So my name is Baptiste. I'm here with the company of Boris as a technical expert. I will explain to you, I will show another language to work with the data that I think you saw this morning. So we are talking about crop monitoring today using a Python programmation language and using a Jupyter Notebook, which is a very convenient format. I know that a group of 40 people can be very heterogeneous, so I'm beginning with the full basis right now. So maybe you can, when it's already done at your computer, you can just listen and you can follow when I'm at your level. I will work in 4 parts, so the whole Jupyter Notebook will be done, but I will tap 4 times, and so I'll speak for 10 to 15 minutes straight. After that, we'll stop for question and answers, so I can have a full speech of one topic at a time. If you have any question, you can already write down in the chat, and if it's a short question, Boris will try to answer to you. If it's an open, long question, we will write it down and keep it after the 10 to 15 minutes, and we will take some pause to answer to your question. So here it is. I'm on my computer and I downloaded all of this data you see from a drive. I already installed Anaconda, which is a software regrouping several packages of programmation utilities. So what I do, if I go to the prompt, Anaconda prompt like this, which is so far empty. So the first step that you should do, but it's already done, I think, in your computer, is to create an environment. So the environment will set all of the packages that you will need for the tools that we will use just now. So the code line would be conda and like environment create f. And after that, you would write down the path to the environment that we gave you. So the file in here, you can open it with a notepad or whatsoever. It is just a list of lots of packages that we will use as add-ons in Python. So this is a list that we did for you. And the whole point is to create an environment based on this information. So if I will use that to create an environment, I will write down the path. So you see that in my computer, so it's all, of course, it's different in every computer. Sorry for my battery, that's it. I will write down this whole path in here like this. And then I will finish with the name of the environment itself, training Riga environment.yml. I won't push into enter because it's already done and it takes a few minutes, but this is how you create your environment. I think it's already done in your computer. So what you can do now is not write this down, but open your prompt and you can check if the environment is actually installed by writing conda and list, and you can press on enter. And by doing this, you'll see all the environments that are installed in your Anaconda software. And we would see that I have the good one in here in my own computer, and I think you should have too. So to select this one, we will activate it by just writing activate and the name of it. So ISA. Yeah. And you can press enter. As I did this, you see that I'm not on the base root anymore. I am on the environment that I created, that Boris created actually for the occasion. And so we are in it. We are set up to begin the session. One other thing, so you all, I think, downloaded those information and it's stored somewhere in your computer. In mine, you can see that I have stored it in my H hard drive, which is a shortcut in here in my own computer. So I would like to go to the H hard drive to access to those data. So I will write it down, H double point, enter. So now I'm in the good environment and I am in my H hard drive. And I'm in the good place now. I can just launch Jupyter Notebook by writing it down. Jupyter Notebook, enter. So it opens a browser. Actually, it opens Firefox mainly, but it doesn't use internet at all. It's just the software that is using the browser as a viewer. So now here I'm actually in my folder. So I'm exactly in the folder of my H in my computer, and I can just navigate to seek for the place where I stored the data. So I stored it in this folder and then in this one, and I am back to the place where I stored everything. You can take this one, so the notebook training to run. You see that it's very, it's not heavy at all because it's empty so far. You can open it and you'll see that the empty script can be run by us, and we will do that right now. So I don't know if you're familiar with this interface, but the notebook is very convenient because we have some boxes like this. And those boxes can be settled as Markdown. So you see that if I double click in this part, it's coded to be text, actually informations. So to quit a box, you can press on Control and Enter. And are the boxes that are actually identified as code. So if I click in this box, you can see that I am in code sessions. So it's succession of Markdown code, and actually could be also text, just root text, to actually define some computations and to add some explanations of what we are going to do. What are we going to do is to analyze some biophysical characteristic in order to monitor crop, maize field, actually. You have lots of information in here saying that we are using lots of packages that have lots of functions, different functions for data visualization, data analysis, geospatial data, whatsoever. Of course, at the very beginning, you don't remember by heart all of these packages. When you will need it, you will use it and you will add it to your code, but you never remember all of this by heart. Here you have a quick reminder of what I just did to launch Jupyter Notebook. And actually the first box of any code is always to launch all of the packages that we will need for this very session. So we install the environment with all of those, and now we are running it to make the use of it right now for this very specific script. So to run a box, you just press on Control and Enter. You'll see that there is a star in here. The star means that it is running. And when I have a number, it just says that it has run and that we can move forward. Of course, we have to follow the order of all the boxes, because one box is creating variable that is useful for the next one. So we always have to go in the right order. You'll see also that in here, after the boxes are created, the output of one box. So we imported lots of packages, but we printed a sentences in here and it appears right here. It means that for the package importation, it's all good for us. So the one and only line that you have to change at your computer is actually this one. This very one, you have to change it at your computer because it's defining the place where you stored the data in your own computer. Once again, this is the place where I stored it in mine. So you see it's still my H hard drive, the name of the folder, and you can stop at the name of this file. So first step for you is to identify where that file is stored in your computer. Take the line in here, copy it, Control C, and then paste it here in the path. And you can stop at backup training data like this. Well, I'll go backward because I had the good path. So I'll leave you like 30 seconds to do so. I think that Python has no problem with slash or backslash, but just to be sure, I'm always using slash. That's good like this. And you see that by adding the main path to the folder backup training data, we will actually do subpath after that, which will lead to vector data, band data, LAI data, because in the folder itself, it's already stored into different data, different folders. So this first box in here is very useful, and I think that all of the all of the data scientists maybe won't use it. It's just a description of all of our data, so you can run it, Control Enter, once you settled your path. If it runs, great. If you have an error message, it means that you may have an error in your path in here, and that you will have to pay attention of all the specific syntax. So you need to end with a slash, and you have to begin with the letter of your hard drive. And so to be sure that you're in the good folder. So this box is just describing the data that we have by having one main path and several subpaths. We have also several lists because it will be very convenient to store every blue band, green band, red band, near infrared band, LAI, raster into lists. So this tool glob glob is actually combining all of the data identified as one specific band into one list, one variable that will be used in further steps. You'll see also that to check if we have enough data, if the path is well done, and etc., we wrote down actually the length of all of those lists. We listed all the bands, and we wanted to know how many elements are present in those lists. By doing so, we wrote down typically sentences that are saying the image list of red bands containing 28, which is constituted by this metric, images. This is a good way to check if our paths, our lists, our data are well settled. We also have two shapefile data that we are using for the session today. One is invariant surfaces. So those are sample polygons of surfaces that won't change during the year, that won't follow seasonal effects, and one shapefile of maze field. More or less 600 maze fields are identified for this session, and we will use them. We wrote down also the coordinate reference system by setting it to UTM-31N for Belgium. This is, of course, very useful to have the same coordinate reference systems if we have different types of data. And in this way, we can check if everything is right. By doing this as well, if you program your script today and you go back to it in 6 months, by just running the box, you just remember very quickly what you did. So help yourself by managing very properly your data, and that will help you for the future. So you can run the next box. And this is an example of figure that we can plot using those visualization. It may take a little time. So two ways to visualize data. You see that in the left in here, I plotted the 5 invariant targets. You have to seek for it a little bit. You have the airport stripes in here that is identified. All the polygons have been drawn in QGIS, and after that, we will load it into the viewer in here. So you have the airport stripes. Actually, the gray one in here is a warehouse. You have the blue one, which is the water. We have a quarry, so stony extraction place. And we have one sample of coniferous forest stand. So we assume that it won't change seasonally as well. So once again, those polygons would be used to assess the stability of all the images. And so we will try to see if in a time series, those polygons, those places that are not supposed to change during the year are actually stable in the optical time series. In the background, actually, we loaded some data from Esri. So you have the line in here that loaded a base map which is made of satellite imagery. And on the right in here, we actually loaded another base map, which is OpenStreetMap. So if you're plotting figures like this, you can always seek for good data online, free, available, that you can use for your visualization. The second sublog that I created in here defined actually the extent of those 5 polygons. So we defined those polygons in QGIS, but if we would like to create a box and an extent of those, we can do so actually. So by extracting the bounds of the invariant polygons, and by creating a box out of it, we can plot it and actually identify what is the region of interest of our analysis. So this is also some examples of code lines that you can reuse for some other projects and that you can use for you. So that was actually last box. So we'll make run last box just to show you the package, which is called Folium. I think it's now. So you can run this last box before a few time for the questions. Oh, my bad, Folium will be later. So this is an example of a regular stack of image that you would meet in your career. If you're analyzing optical images, actually you'll have lots of them which are cloud-free, but you can also have lots of clouds in your images. So this is an example of the only image actually that we had in our stack and that we would remove that after that. For the example, of course, this check of clouds is very, very useful when you do data analysis, especially in our region, in Europe, when, I don't know the weather of Riga actually, but I'm sure that as in the center of Europe, it's very cloudy, not most of the time, but sometimes during the year. So the check of those clouds is very useful, and this step is actually needs to be done. So once again, in here, we use the lists. So remember the list that we created, the list with all the red bands, the green bands, and the blue bands in here as well. And we selected the 5th one for this one, for the cloud-free images, and the first one that we identified as the only one with cloud, just to show you the picture in here. So this is another way to plot optical figure and to analyze your data before processing it. I will already stop now for a few questions because I don't know if I was very quick or too slow or too detailed or not detailed enough. So I will leave you to 7 minutes question maybe. I don't know if Boris had some questions in the chat. Okay. Okay. Seems to be all right. J'arrive pas à voir le chat et mon écran en même temps en fait.
So I have a participant who's having an error in, I think, the first cell. If you don't mind, he could share his screen and then get your help.
Of course you can.
Okay.
Yes. You can just try to add a slash at the end of backup training data. Yes,
Okay.
just add a slash or backslash and run it again. Okay, no, so the path is not. Ouais. There is an apostrophe that is. Is there something after training data backslash apostrophe? After that, is there something? Yeah, an element after that. Try to delete after that, or no, you can leave it like this.
Change order of slashes. Uslete, yeah.
You have backward slashes?
Yes.
Oh, okay.
You need all backward
Forward slashes. Yeah, so it's regular slashes. Backward. I'm sorry. So backslash doesn't work. Sometimes it's okay for the main path, maybe not. So try to use forward slashes. Thank you for Alex. Right, and for going at the next line.
So a new question is coming in.
Perfect.
Okay, sorry, you can talk.
All right. Have you loaded the environment actually before launching Jupyter Notebook? Because normally it's actually set in the environment, but you have to activate the environment first.
Is that part of the code here, or do you mean
No, before you
in Anaconda?
Okay.
Yeah, you would open the prompt, or in here you can actually
This one?
select this one. Yeah, select this one. You're in the base root. If you select Isariga, wait for it, and then actually you can close the notebook that you opened. You can close everything and reopen Jupyter Notebook when this environment would be set and relaunch everything. In this one, everything is fine. So you can go back to home at the left of your software. Yes, you can close this one. You can close the notebook. Just close it. Close it completely. This one as well. Yes, and then go back to Anaconda. If you click on home on your left, yes, now you can relaunch Jupyter Notebook and with the right environment.
All right. I'm not sure where you downloaded the notebook. Okay, so we have several people who are at this stage. They had to close and reopen again, or they started late and they don't know exactly where to click. If you don't mind explaining for everyone.
If they can't find their data at this very point, either they know where they are stored in the computer, maybe in the documents or in the downloads, and then they can look for it by double-clicking in the folder in here. Or if it's stored in another hard drive, not in the C, you should go by the prompt. I can show it once again if you want.
Yes, 1 minute.
I think, yeah, you can just close this window. Yeah, and this is right. Perfect.
So which one would it be?
The to run, the first one.
The first
To run. So the first one is empty and we can make it run.
Okay. So that's it, and now she can start running the first cells and catch up.
Perfect. You can make run only the code part, so the packages and the data storage. So the packages are a little bit lower. Yes, you can click in it and then click in the box and then press on. Yes, that's it. Looks okay, perfect for the environment. And for the second one, remember that you just have to change the path to your own computer. So when it's written walk path, Maybe the one in red below, work path equal to, and the red one, you can change it. Oh yeah, I will explain that to you after that. Comment tu dis? Ah ouais. Même en musique? Yes, that's... maybe you should unzip it. I mean, so the folder that you seek in here is the folder with the images.
Oh, okay. Can I...
So maybe not this one. It's maybe also in your downloads.
So she's going to be looking at probably this
Yes,
one, right?
yes, this one. But you can just... Perfect, stop. You can, yeah, copy all of these
Okay.
and put it there and change your backslash to forward slashes.
Okay.
And that would be perfect, I
So,
think.
here. And this needs to be changed to forward. Exactly, everywhere. And then you can run it.
All right. Try to make it run.
Okay, let's run and it finishes. All right.
Yes, perfect.
Okay. Is this as far as you got? She stops here?
Yeah, it's
Okay.
perfect. Yeah, we can continue.
Yes. Okay, I'm going to check something.
So here I'm back. So what I forgot to tell you also is that when you put a hashtag like this, we call it to comment a line. If I comment a line, it means that it won't be used as a script. So it's just a commentary of the section. You see that here I use this as a title. So if you want, in this very script, you can add your own commentary. Actually, you can, if you want, so you have to use these hashtags and to write at this point, he explained that blah, blah, blah. If you want to add any commentaries. So don't hesitate to do that in your own script. If you put an hashtag, it won't be considered as code. That's it. Sometimes we added hashtags ourselves just to show you the line and to give you the opportunity to remove the hashtag if you want to run the line and to leave it if you don't want to run it. So we'll continue with that. So you RGB list. So we saw that we had several images, cloud-free or cloudy, and that we should manage this. So the 2 or 3 next blocks, actually, we are not going to run it together because you saw that the time is very short for our session, but we put for you some lines to use a Send-to-Core mask, because maybe you will download some Sentinel-2 images processed with Send-to-Core mask. And in the Send-to-Core folder, you actually have a SIM classification, so a raw classification of the territory, which classifies the images into big classes, considering no data, saturated pixels, shadows, cloud shadows, water, unclassified snow, etc., etc. This is a raw classification, so not convenient to do like land cover or precise land cover, but it's very used to show the cloud on an image. And so once again, we won't do it together, and we selected cloud-free images just for you. But if you're using Send-to-Core folder, you can use the script actually by just using this like this and replacing the path that we indicated over at the beginning of the script. You can actually replace in your images everywhere there is a 0 of a 1 or a 2 or 1, 0, sorry, everywhere there is a 0, 1, 3, 8, 9, 10, 11 by not a number, so but by no data value. Replacing a pixel by no data value makes it not to be considered in further processing. If we construct a raster value with pixel value of 1, it will conserve the pixel value of the original images. So you see that the categories in here, for an example, if I take 0 and 1, I see that we would consider no data or saturated or defective pixel as no data value. Cloud shadows, of course, also as no data value. So this is a process to actually remove or to mask the cloud of your images. The bugs are in here and proposed to you if you use them to core in further steps. I'll go further by introducing you to Folium library. So this is a pretty new library that is available with Python. If you run the box, Control Enter, you'll see that we once again selected one red band, one green band, and one blue band. And we loaded some data online from the ArcGIS server. It takes a little time to run, but you'll see that the Folium library allows us to have a dynamic map, actually. So you've seen here that now you have a figure where you can zoom in or out. You can plot actually your data. For us, we actually plotted those 3 bands, the 5th one of the red list, the 5th one of the green list, and the 5th one of the blue list. It constituted spectral bands of the same images, and if you go over there, you can see that you can light up those bands one after the other, like this. So it's opposite sides next to GIS softwares. It's from below to up. So if you zoom into the field, you'll see that the spectral band, so the band 2 is blue in Sentinel-2, and that we have some reflectances in some fields corresponding to, you see that the vegetated area are very dark because the blue is actually not very present in the vegetation. If I light up band 3, this is the green band, still very dark. And some places are highlighted, so the spectral signature may be different in this spectral band, and in the band 4, which is the red band, we'll see that still the reflectance is very high at some places and very low at other places. So the whole point of this box is to introduce you to this type of visualization. So you have lots of parameters in here. So we defined actually the point where the images will be centered. This is the center of the image to show where to see it. The bottom the bottom, the top, the left and the right of the images have been defined as well. And actually we have some let's say buffer that has been defined to visualize the image. So if I make it run, it will actually appear with those buffer information on the image on the first place before I zoom in or out. So I relaunch it. Yes. All right. So basically, we would consider centering it a little bit better, but so far it's nice to actually see your data in this dynamic viewer. Let's go further. So the whole point of our session in here is to compute mean surface reflectance of maze field that we sampled earlier. So first of all, you can actually launch your box to see what is inside of it. We will focus on the invariant targets. So before computing the reflectance of maze itself, we will try to see for optical data set is stable, has stable value. So we will actually use our 5 invariant target that we had identified as stable. So we will consider that those 5 places are stable during the year, and that we will see through our time series if the reflectance value are actually stable. So we loaded the spectral information. So in every polygons, we extracted the mean value of reflectance data, and we can actually now, if you launch the next box, we can assess if we had some no data value in those polygons, which means we extracted the mean value, and we also assessed if in the polygons we had some no data pixels. If there are some no data pixel, it means that the sample at that very specific date may be useless. Maybe at that very specific date we have peculiar artifacts, or maybe there is a problem with that polygons. We can see in here that we had no non-valid dates for all of the polygons. Once again, we sorted it before to have cloud-free time series just for this session. So usually you would have lots of invalid dates or polygons at a very specific date because of the remnant clouds in all of the sky. So basically, that's a pretty good start for us. We can continue like this, and we are now plotting the surface reflectance into time series for blue, green, and red bands. So first, don't forget to launch the very small box in here, which creates an empty list. So we first create an empty list in which we store actually mean reflectance extraction in order to put them into time series. The 3 next boxes are pretty much the same, actually. So you can run the first one, and you'll see that for the first blue band, up, we have 5 figures that have been plotted. So remember all 5 polygons. We had water, quarry, warehouse roof, pine trees, and airport track. And we can see that through the year, it's pretty stable, but we have some variation. So what can you see in this figure? Actually, you see the green line is actually the median value of all of the samples. We also defined the threshold. So we defined it by, in here it's 0.15. So we define it because below that value, we would consider that is just some noise inherent of the sensor. Below that threshold, we would consider that there is a problem. There is an external problem, and that probably the optical data wouldn't be considered as good data for our process. It actually depends on the process that you would like to define, and the threshold can be actually changed. So if I have a more severe threshold, of course, I would have more outliers. So the whole point in here is to try to see if all of the images are inside of the threshold that we consider as stable, or if they are out of this threshold. So for an example, for water, we can see that we have 2 dates where value actually are way higher the threshold. So we would consider looking at those images and checking if the polygon is problematic, if there is maybe a small cloud that we hadn't seen, there is a problem with the pixel, or if whatsoever, maybe there is a boat going at that very specific time. Same thing for the pine trees and for the airport tracks. So we'll see that we have lots of outliers. So data value that are actually not very satisfying. So I will set back my threshold to 1.015 as it was set. All right. For the quarry and the warehouse roof, we have something peculiar in here because we see that we have kind of a seasonal trend, actually. So we thought that we had some stable targets, but actually we are observing a seasonal trend. This is actually, so we haven't gone on the field, so maybe in the quarry there are some vegetation growing during the season, and maybe in the warehouse as well. I don't know, maybe this is a green warehouse, maybe they installed a green rooftop between the time when we took the picture and at the time when we did our process. But actually, these are not relevant figures, because we can see that what we define as stable targets are not that stable, actually. We identified outliers in the 3 other stable targets, but those targets depends on the process that we would do. So it doesn't mean that this date is necessary out of the boundary and useless. It means that we should pay attention, maybe look at the picture, maybe, and decide, shall we keep it or shall we remove it? If you run the 2 following boxes, you'll see that the same exercise have been done for the green band, and we have the same trends actually that we just discussed, and also for the red bands. And if you compare the figures of one band between another, you'll see that actually the trends are exactly the same. So the outliers are coming from the same dates, and the seasonal trends are also visible in the quarry and the warehouse roof. Once again, it identifies some questionable pictures. It doesn't remove them automatically. So what we can do right now is do some proper synthesis of what we just observed. If you run the next block, you can actually print. You see that there is a for buckle in here, a for loop, sorry. And we identified actually that at some point, some dates have been detected as outliers lots of times. Some dates have been defined as outliers a few times, and then we could actually add a new threshold by deciding, okay, if an image has been detected as an outlier more than 5 times, we should remove it. Maybe there are some problem in the spectral signature. Maybe there are some atmospheric aerosol that we didn't remove with the cloud mask. Maybe we have a problem. And so keep in mind that if we are programming and coding things, is to help you when you'll have 500,000, no, not 500,000, but 500 or 1,000 images to process. If your code is well settled, having automatic decision for you, it helps a lot. If you have 5 or 10 images, you can go through softwares, but programming is very helpful when you have big data storage. I will stop. I will do the second step for the time. I don't know if you have any question or if things has to be better explained. The mic is yours. So all the optical images have been pre-processed for us to have actually normalized optical signature. What we do with the stable target is that we check if the signal is very stable, is actually stable. We don't trust actually the pre-processing, we check it. And by doing this, we suggest a threshold, and that threshold once again comes from the literature review, from the sensor sensitivity. And when we have outliers, so data value outside of this threshold, actually it activates an alarm for us. We should pay attention to those dates. Is there a problem? Shall we open it? Shall we see? Shall we check? And that's actually something that we should do to check if our data set is stable, relevant, robust, and if we could carry on with those data. I don't know if I answered your question. Cool. There are no really we don't have a proper transition between the first step that we just ran and the next one. So the first one is actually to help you manage your own raw data if you're downloading some in your own initiative, but actually to continue with the third part, we had also a time series of clean LAI. I think that you saw what our leaf area index this very morning. And we are actually using a clean time series. So we didn't remove any date and we are carrying on with the data that we have, but you have all the tool and the boxes and the programmation line to spot and to repair the data that are problematic. So now we are exploring time series analysis of leaf area index. So you saw that this is a physical measurement of the health of a crop, and that measuring this metric is actually a good indicator of the productivity of a field. So if you run the first block, you will see that we defined once again the extent of the region of interest that we will work on, still using the shapefile of the field maze that we have, and by extracting the bounds, creating a box out of it and plotting it, we just identify the region where we are going to work. As I told you, if we could actually, in our list of LAI images, so we already actually create that LAI list, because at the very beginning of the script, just look at me, don't go there. At the second box, we actually listed the blue band, green band, red band, and the LAI band. So those are stored in here. We can use them, and that's what we are doing in here. Just to have some viewing of those data, we are actually selecting the 15th one, the 16th one, and the 20th one to actually be plotted and to observe is there is a big change in leaf area index from a period to another. We see that by selecting them, we can also print the dates. So we selected the 15th of May, 1st of June, and the mid-September. So right in the growing season, and one date in the senescence season. So if we plot those raster data, what can we see? Still using the Folium dynamic package and plotting our tree LAI on it. What can we observe? All right, we still have our dynamic viewer in here. You can see if I open the first one first here. This is the leaf area index, and as we may know, the high value correspond to the places where we have lots of vegetation in good health and well developed. So for the 15th of May, it may be some late winter cover that are still there and that haven't been harvested yet. If we go further in the growing season, you see that in the 1st of June, lots of crops are actually growing and that the leaf area index is increasing in lots of parcels. We can go further to mid-September by seeing that this is the end of the growing season and that lots of field correspond to high value considering their leaf area index. And so those three bands can be observed manually through your viewers. This is the same idea as the box to manage your data. Even though you're doing only processes, try to plot regular figures and to observe what then you have and to be sure that you're not processing blindly and actually check, do visual check of your data. So what shall we do here? We had a region of interest defined for analyzes the leaf area index. We will try to see if we could combine those three leaf area index of three different dates into one RGB images, and we can. This is pretty peculiar because you see that this image is not really an image that we could observe in the reality, because this is the combination of 3 bands corresponding to 3 different dates. So red is actually the 15th of May, green is the 1st of June, and blue is the 14th of September. So you can actually combine 3 raster data of any data from different periods, and you can combine them to RGB images. And it can actually show you the fact that all of the blue fields, blue would be actually the highest value of September that have low value during June and May. So maybe some begin of winter wheat or winter cover whatsoever. In June, you'll have the high value in red. So it means that most of the field in here actually show their peak of vegetation in the 1st of June in the comparison of these 3 dates. So once again, it's a peculiar visualization, but it's a good opportunity to combine data and to show a new reality of crop cover. Now we will look at the shapefile that we have. So we define lots of maize parcels. So we can see in here that we have 614 maize parcels in the shapefile. So this is a lot. So the code line in here just selected a fifth of them, just 20% of them had to be selected just to reduce the processing time and the processing resources. The second parameter is actually a random selection of 20% of those parcels. And if I put 2 or 3 or 4 or 5, this is another random selection. But by using 1, I can still use the random selection 1 and use the same random selection from one variable to another. So we just selected 20% of our parcels that are coming from a shapefile and have been translated into a geodata frame. And that's our samples. The whole point now is to visualize the seasonal crop through LAI evolution, and that's what we will do now. We will compute mean LAI inside of every polygons, and we will draw time series to observe the seasonal crop. We can run the next box. So to do so, we actually have to combine all of the leaf area index into one TIFF file with many bands. So actually we'll have so we had 28 leaf area index, and we had to combine them to one TIFF file with 28 bands. This is how we can easily plot time series. So this is just a data management step. And as we did that, we can go further. Takes a little bit of time. If you're not programming often, you will learn that actually the software itself and the code is very light. But what makes it very heavy is the size of the data that you're processing, of course, which means that you can easily install Anaconda on your personal computer. What is very inconvenient in personal computer is to run big data, actually. So that's it. Lots of time for, it looks like not a lot, but it is a lot, actually. It created a matrix with 123 time series, which constitute 123 field samples that we selected, and we have the 123 time series inside of it. So as we gathered all of those data into one matrix, we can now look for it, and we can plot it into graphical information. So first, don't forget to run this one. It just translates a column into line, invert column into line, because it's more convenient to plot time series. And now if you launch the next box, you will see once again a check that our image is well LAI images. So we are fine like this. We just combined all of the leaf area index data into one stack. We inverted the column and the line to plot time series. And that we did so actually launch all of the boxes. You will see that this is the result of those combination. We have a very big data frame with all of the dates constituting all of the lines and all of the sample numbers constituting the column. So we can see that for one very specific field, we have all of the LAI value of the whole year, the whole actually time series of the optical images that we have. It takes a little bit of time to process this, but this is actually the richest part of the data that we created so far. And this is very useful for the analysis that we will run right now. Using this, we can carry on by plotting this that looks a little bit confused, but it's actually not. This is the time series of the leaf area, all the leaf area index value of all the samples through the year. What can we see? We can see that, so this is also a dynamic actually figure. So you can double click on one if you want to see only one growing curve, and you can double click on it to show everything. We can see that actually this is the growing season of maize. What we can see before and after maybe are constituted by by some other crops. So we can look at those growing season, but this is considered as winter crops, winter cover, and we won't need to use those signature for our processes. So the first step that we will do is to reduce our time series into the dates that are interested to us. So we can run the next box. All right, and by reducing the date to our growing season, actually it's a little bit too low, so you can change in your box to the 15th of May. All right, so this is typically the time series of the growing season of maize. So basically we have all of our samples in here. You see that we also computed the mean that you can light or shut, and the 25th and the 75th percentile, considering the highest and the lowest samples. I will once again stop for a few minutes. It's actually quite an exercise for me to speak in English, and I need to drink lots of water to keep my voice. So I leave the chat to you and Boris, but you can also take the mic and speak out loud to have any questions.
Someone asked where the shapefiles came from.
So the shapefile is actually in the folder. So actually, it's impossible to delineate 600. Tu sais expliquer? So Boris will answer to you.
All right. So the shapefile we used in the notebook comes from an administrative declaration that's compulsory for every farmer in Belgium, in which they have to declare the administrative limits of their parcels, as well as the crop that's grown on it. And that's updated in a yearly manner, which is quite helpful because it's a golden source of data. So that's where it comes from. I don't know if I was clear enough.
And to carry on with what Boris just said, of course, if you have 10 parcels, you can go by yourself with your GPS and take the measurements on the field. If you have hundreds of them, you need to seek some shapefile from some public administration. All right, so I will give the final explanation to Boris, as I'm losing my voice. And yeah, for the last lines and the last steps, Boris, the floor is yours.
Right. So we computed the reduced time series, which covered the whole growing season. So from the beginning of June until the senescence phase at the end of October and beginning of November. So now the metric that we're going to use to assess the quality of the crop growth cycle is the area under the growing season. So what do I mean by that? So the area under each time series curve will be computed. So for example, we'll compute the area under this green curve, and then using the distribution of all the area under the curves, we'll assess the crop growth quality. So the first thing to do is to compute said area under the curves. So what you can see here is all the area under the curves of each time series. So that's the first one, that's the second one. And so logically, there should be 123 area under the curves corresponding to the 123 parcels. So we can then use these metrics and store them in a data frame, and we can look at the distribution of the area under the curves. So what we can see is that we have very few parcels with a low metric of area under the curve, and that the distribution is almost normal, with a mean that should be around a value of 15, which doesn't really have units since it's an area. And so you can see that we have 50 parcels in this category, which is the most frequent one. The next step consists of the preparation of 5 data frames. So data frames are a convenient way of storing data using pandas, which is a Python package that is in the environment. So what we will do is use the percentiles. So each parcel having an area under the curve of the LAI time series with a value below the percentile 15 will have a quality. So that's the name of the metric, stated as very low. And the same process can be repeated using intervals. So the intervals are the percentile 15, 20, 40, 60, and then 80. So if we run the block, we can see when we display the very low quality data frame that we have the identifier of the parcel, as well as the dates of the time series, and the very low quality, which was assessed using percentiles. So now we will concatenate those 5 data frames into one big table, allowing us to further analyze the crop growth cycle. So what we will do here is a little exercise of visualization, which will allow us to assess the quality of the metric and to know if it's really relevant or not. So what was done here was to to set a color according to the metric. So if the parcel was assessed as really good, the color blue was used, and so on. So you have a table that summarizes this all here. So the very low time series are the red lines, the low ones are the oranges, medium yellow, and the high quality parcels are the green lines. And so what we can see here is that the metric is quite relevant, except for the low and very low time series, which have quite confusing profiles. But the metric is quite strong for the parcels that have broad and high amplitude of crop growth cycle, so the blue and green lines. So now we will store this in another table, which will allow us to export this data in the form of a shapefile. And this will allow you to further examine it and look at these parcels on QGIS. Oh, yes. So here, when you put 3 apostrophes at the beginning and at the end of a block, it's the same as if each line had a hashtag before it, and it's used to comment a big chunk of codes without having to comment each line individually. So we can further run this block, and we now have a final table with the ID of each parcel, its surface, the crop name, which is all maize, the geometry and the quality, and this can then be exported as a shapefile. So you can uncomment and remove these apostrophes if you want to export them. And finally, what we can do is take a subset of this final table and take a look at the LAI of a few different parcels at the peak of their growing cycle. So I will illustrate further. So now we have taken a subset of the very low quality parcels, of the medium quality parcels, and of the very high quality parcels. And we are going to take a look at the parcel and its LAI at the peak of the crop growth cycle. So the first step is to determine when the peak occurs. So we see that the maximum of the LAI of the very low labeled parcel is obtained at the beginning of August, of the medium labeled parcel at the end of July, and of the very, very high labeled parcel at the beginning of August. And now what we can do is plot these parcels to see, this step takes a little bit of time, to see what their LAI was at the peak. So we see clearly that there is a clear difference between the very low quality parcels, which have a very low LAI at the peak of the core growth cycle, compared to the very high, which are clearly well vegetated with a strong vegetated cover. So I might leave the floor to Baptiste for the conclusion.
Yes, thank you, Boris. So if I may add some comments concerning the heterogeneity of a parcel, those figures are very useful to see 2 things. First of all, we can see that in some parcels, the heterogeneity could give some indication to the farmer, saying that there is a specific points where the growing didn't happen quite well. So maybe there is a problem here. Maybe they had some problem in water accessibility. Maybe the soil is not that good at that very place. Maybe there is a practice that should be not done next year. We can see also that concerning the samples that we used, sometimes we should have added a negative buffer because for the mean value of this whole sample, actually we are adding a very low value that are constituted as the path actually between two parcels. So maybe yeah, a negative buffer would ensure to have the proper value of the field itself, and to consider better information through LAI. So final word, of course, when you have those figures like this, you can go back to the growing curves. For an example, if you remember 2,534 next to this one, 1,137. And if we go back to the curves that we had illustrating the time series, we could actually select those samples. So if I go to this, the lowest one, which was 1,137, red line, yes, this is the one. All right, if I compare it to the highest one in the blue line, 2,534, yes. And here we can see that actually the metric of the area inside of the curve is actually not that bad, and it's sometimes working quite well. So you can go back and forward from your figure to your time series and to observe actually the growing season and the growing evolution of your field through LAI analysis. That's pretty much enough for us. We still have 3 minutes for questions. We understand that we were very quick by describing all of these. The point for us is to give as many tools, as many boxes, as many programmation process that we can. We would advise you to be very slow to rerun it by yourself. So take your time to understand every parameters, try to take some part of it and to replace it into your own code, and little by little you will jungle more and more with those programmation processes. So the mic is yours. Is there, and the chat is yours. Is there any questions? Could the low LAI be correlated with smaller area in this case? You're welcome, Alexandre. Alex, yes, it could be, but mostly because we have a few pixels of high value constituting good health of the crops. So maybe if we would do a negative buffer of minus 20 meters, for an example, we would remove that eventuality. But maybe the smaller area can also constitute a parcel that is between a road and a bridge, maybe an area of lesser value. I mean, in soil, in not a good value of soil, of water accessibility or whatsoever. So maybe this is a small parcel that we cultivate anyway, but that we wouldn't consider as the best productivity in the area. So you can try to make it correlate actually to plot to plot a scatter plot with the area in the X and the LAI value in the Y, and try to see if it's correlated, maybe. But this is not the only indicator, probably. Thank you, and also thank you for the great practical calls and the amazing use. You're welcome. Actually, this is Boris who designed it, so thank you, Boris. And we sure hope that it would be useful for all of you. Nice, great, Boris. Yes, thank you, Alex.
So, are there other questions apart from Alex? Before Baptiste disappears?
Thank you, Robert.
Okay, so if there are no more questions, the session is closed. Thanks, Baptiste. Thanks, Pierre. Thanks, who was helping you? Boris. Yeah. And I hope you maybe can keep in touch with the students if you have provided an email so that they can ask more questions if they happen to have other questions tomorrow or the day after.
Sure. The more convenient if you group maybe questions and we can try to answer to what we can from the distance, but don't hesitate to do that, of course.
Yeah. Okay. So then the other option is if you have more questions, you send them to Amalia. Maybe she can put them together and send all together to you then.
Perfect idea. Great.
Okay. And then I think that you all have been recorded, so students can still access the videos in the future if you wish to redo the exercises or rerun the exercises and so on. So thanks, Baptiste. Thanks, Boris. And we see each other tomorrow for the next lecture, which will be on it's on radar applications for ground motions with Ramon Hansen.
Welcome. Good luck to everyone. Bye.
Bye-bye.